Okay, so the first topic we're going to cover in this course is the problem of language modeling. Language modeling is one of the oldest problems studied in statistical natural language processing. It's a very basic problem, and it's a very useful problem. Language models are used in a very wide range of natural language applications. So we're going to cover a number of things. I'm firstly going to define the basic problem. We'll then talk about a very important class of language models. These are called trigram language models. These are extremely widely used. We'll talk about how to evaluate different language models, how to measure the effectiveness of different language models. And then finally, we'll talk about a couple of estimation techniques for language modeling. Firstly, something called linear interpolation, and secondly, something called discounting methods. Both of these methods are widely used within language modeling, and as we'll see later in the class, they're also useful in many other problems in natural language processing. So these basic estimation techniques are widely used in other areas. So to get us started, here are a couple of definitions. We're going to assume that we have some set V, and this is a finite set, and this is going to include all of the words in our language of interest. So imagine we're constructing a language model for English, for example. We might have a set V containing words such as the, a, man, telescope, and so on and so on. And it's not uncommon for this set to be really quite large. It might easily contain thousands or tens of thousands of possible words in the language. So given this underlying set V, I'm going to use V dagger, this symbol here, to refer to the set of all possible sentences or strings in this language. And a well-formed sentence takes the following form. It has 0 or more words, where each word is drawn from the set V, followed by a special symbol, the stop symbol. Okay? So the use of this stop symbol at the end of each sentence is initially going to look a little peculiar, but we'll see soon why it's very convenient to include this symbol when we start to develop a probabilistic model for the language modeling problem. So just to recap, a sentence could have any sequence of words. It could be a sentence that makes sense, for example, this sentence here, or it might be some sentence that really doesn't make sense. We could have sequences like the, stop. So any sequence of words drawn from this vocabulary followed by stop. And we'll also include a sentence where we have the stop symbol alone. This is the case where the sentence is basically of 0 length. There are no words before stop, just to be completely precise. So given these definitions, we can now define the language modeling problem. So I'm going to assume that we have a training sample of example sentences in the language we're interested in. Let's just assume that's English for now. So for example, you might collect all sentences that you've seen in the New York Times over the last 10 years. Or you might collect a very large set of example sentences from the World Wide Web, and you can think of many other examples. And this training sample can again be quite large. So to be concrete, in the mid-90s, for example, it was pretty common to make use of roughly 20 million words of data in these training samples. And by the end of the 90s, it wasn't uncommon to use maybe 1 billion words, often again chosen from newspaper data, for example. And more recently, over the last several years, people have started using web data to construct language models. And we might even get into a scenario where we have hundreds of billions of words of potential training data. Now, the main point here is just that these training examples can get quite large. So given a training sample, our task is the following. We want to learn a distribution, P, over sentences in our language. Okay, so P is going to be a function, and it satisfies 2 conditions. So firstly, for any sentence X, Remember, V dagger is the set of possible sentences in the language. For any sentence x, we have P of x is greater than or equal to 0. And secondly, if we sum over all sentences in the language, we have something that sums to the value 1. Okay? So P is a well-formed distribution over sentences in the language. So our task is going to be to take a training sample of example sentences as input and output some function P as the output of this process. So here are some examples. We might, for example, assign the probability 10 to the minus 12 to the sentence composed of just the word the followed by stop. We might assign 2 times 10 to the minus 8 to this particular sentence, and so on and so on. We just assign a probability to every sentence in the language. Now, roughly speaking, we would like a good language model to assign high probability to sentences which are likely in English and low probability to sentences which are unlikely in English. So, for example, this sentence here is pretty ill-formed. You're relatively unlikely to see this as a sentence, and that has relatively low probability.